Hello, my name is Matthew Schuh, and I'm here on behalf of the co-authors Maximilien Dupont de Dinechin, Mathieu Moi, and Claire Maiza to present you our joint work entitled Scaling Up the Memory Interference Analysis for Hard Real-Time Many-Core Systems. As the title states, we're inserted into a real-time systems domain, where the execution time of programs must remain predictable to ensure the respect of the specification deadline. Multi or many-core architectures with shared resources make computing the worst-case execution time harder, because we must take into account the interference generated by memory accesses. Our software environment comes from data flow applications, and we try to fix the release dates, ensuring the respect to the dependencies. We started from an existing algorithm that did this computation in O to the 4, and I will explain you how we've managed to improve it. So basically in this work, we're exploring how to solve the interference computation problem that arises from simultaneous accesses from several cores to one shared resource at a time. As an input to this problem, we receive a task set that is a directed acyclic graph, or DAG, obtained from high-level data flow languages. We can then automatically extract the task dependencies from these languages, and we assume that the order, mapping, and worst-case execution time, or WVCT, in isolation are given to us. Here in the left figure, we can see a DAG example that will be used in the next few slides. The vertices being the tasks with the number of memory operations from one task to another on the edges. And here in the right, we can see the mapping of tasks to the cores, here called processing elements, and also their WVCT. The interference in many-core architecture comes from the fact that we have several initiators trying to access the same resource, which in our case is the memory. This access is controlled by hardware arbiters that implement different policies and that can have a huge impact on the task's execution time, according to the workload or the number of initiators sending requests. Here in the left figure, we can see the path that cores need to go through in order to reach a memory bank, and in particular, the bus arbiter mechanism. Here in the right, we have a more in-depth view of a bus arbiter studied in our paper, the MPPA2 from Colray, that is composed of several arbitration levels and even different arbitration policies to decide which request is granted first to the memory bank. Our goal in the end is to have a static time trigger schedule in order to minimize, by construction, as much interference as possible between the tasks. For this, we produce precise release dates for the tasks, allowing us to control the interference and have a safe bound on the worst-case response time, or WVCRT, of the program. The left diagram shows us a schedule where the interference was completely ignored, and the total execution time was of 6 time slots. And here on the right, the interference is taken into account with the number of memory operations from slide 3, and we can see that in particular, tasks N2 and N4 started 1 time slot later because of the interference, increasing the execution time to 7 time slots. This works based on an original algorithm that computed this interference using global fixed point iterations. The first iteration computed the response time, which is the execution time plus interference, and then it adjusted the release dates to respect the dependencies and avoid any overlap between tasks on the same core. This global approach led to a high complexity of O to the 4, and the fixed point is hard to reach in this algorithm because the interference and execution time are interdependent problems, Changing the execution time and the release dates may end up changing the interference between the tasks, and so on and so forth. So here we have an overview of how this algorithm works. It takes the inputs that we've mentioned in the first slides, the task set, their dependencies, ordering mapping onto the course, and then it goes to step 1 and 2. In step 1, it estimates the current interference with an initial set of release dates, and in step 2, it adjusts the release dates of the tasks so they do not overlap and they still respect the dependencies. The algorithm then repeats steps 1 and 2 until no interference is added and no release date is changed, and then it finally checks the schedulability of the task set in regard to the global deadline. Our improved algorithm takes a different approach and computes the schedule in an incremental manner. We use a notion of time cursor that progresses forwards in time, and we schedule one task at a time. We know that we can release a task when its dependencies are satisfied, and if we're after its minimal release date if it exists. And then once we schedule a task, its release date is fixed and won't change later on. And it's only at this moment that we compute the interference impact of adding this task in particular onto the subset of currently running tasks. This approach reduced our complexity to O(n)(, and we are able to easily schedule thousands of tasks, which was not possible with the original algorithm. Here we have a snapshot of the algorithm, and we can see the time cursor in red. And at this moment, the group of alive tasks is N0, N4, N7, and N9. And the tasks that we won't bother to take into account are the dead ones, N3, N5, N6, and N8, and the future ones, N1, N2, and N10. This time cursor starts at T0 and keeps advancing either to the next minimal release date or to the next finish date of tasks. The dead and future tasks cannot provoke interference or change the response time that is being computed for the currently alive tasks. So we have our improved algorithm with a good theoretical complexity. Now, how does it perform in practice? To measure this, we've evaluated our algorithm with randomly generated task sets that try to stress the algorithm as much as possible with also random double VCTs and a random number of memory accesses. In these graphs, we can see our benchmark results. In the y-axis, we have the time spent running the response time computation, and in the x-axis, the number of nodes in the task set. We can see that our algorithm in red outperforms the original one after less than 100 of nodes. It actually performs poorly for a small number of nodes due to the Python interpreter overhead. It's also noticeable the vertical shift between the two curves as the number of tasks keeps increasing. And this shows that the improved version is able to tackle way bigger problems in reasonable time, where the old algorithm would simply take too long. You can also notice that the new algorithm always stays under the theoretical complexity of O(n)(. And in this particular benchmark, we can see almost 600 times faster execution time than the original one. So to conclude, I've presented you an interference analysis algorithm in O(n)(, for many core response time computation, able to quickly schedule thousands of tasks which represent a huge improvement over the original algorithm which this work was based upon. And as future work, we foresee the treatment of overlap between tasks running on the same course, as in this moment the algorithm considers them as a single big task in order to compute the interference. Dealing with this overlap can actually reduce the pessimism introduced in the response time computation. So thanks for your attention. You can download the full paper at the following URL or scanning this QR code. And if you have any further questions about the paper or the presentation, I am reachable in the following email addresses.